So we've learned a lot about the idea of stereochemistry and our stereoisomers and describing chiral centers. But one of the big questions that we finally need to answer is how do we incorporate that information into our nomenclature, our naming? Because, for example, if we see here, if I simply say 2-bromobutane, it's going to be a 4-carbon backbone that has a bromine off of it, but you don't know any information about the stereochemistry. And depending on if there's a wedge to a bromine or a dash to a bromine, that's going to change between your R and your S configuration, and that can have drastically different properties. So just the name of 2-bromobutane is ambiguous. It doesn't give us enough information to differentiate between the appropriate stereochemistry. So in order to differentiate between those structures, there are going to be a few extra prefixes which we can use to be able to effectively describe the entire molecule with the appropriate stereochemistry. And for this, we're going to have 3 primary classes. Our very first class is going to be the one that's going to be the most limited, meaning it cannot be used in a lot of situations. There's only going to be a few specific spots where we're able to use that, and those are going to be our cis and trans. We talked about this a decent amount when we were thinking about drawing our chairs in our last unit, and we're going to go ahead and formalize that incorporation into our naming system here. Our second class is going to be where we have our chiral centers. Those are going to be a atom, often in our case, it's going to be a carbon that has 4 unique attachments, and we can use our R and S configuration. And our last is actually going to be describing double bonds. And these are going to be 2 new words that we're going to spend the majority of the video focusing on, of E and Z. So the cis, trans, R and S, E and Z are all going to be our descriptors for how we can describe our stereochemistry. All of these are going to be prefixes, so these are going to go all the way to the beginning of the name. And let's go and kind of look through a variety of these. So our very first one, or our class 1, are going to be examples for kind of 2 main classes. The first are going to be rings, and the second one is going to be double bonds. And these are going to be cases where we can use the cis and the trans. So cis is going to come from the description of same. So if something is cis, you're going to share the same stereochemistry. So in a cyclohexane ring, for example, if we say cis, we mean both of them are going to share the same wedge or dash. Trans is going to be the opposite, where one is a wedge, one is a dash. Now, one of the reasons why these are a little bit more limited is because you actually don't necessarily get down just to the individual structure. You get down to typically one of 2. So for example, if I say cis 1-isopropyl 3-methyl cyclohexane, that's the name for this first structure here, it could be wedge-wedge, or it could be dash-dash. Differentiating between those is not possible. For all of these, you can actually use your additional classes. So for all of your class 1A, we can also use R and S, which is going to be our class 2. And then for our simple alkanes, we can also use E and Z. That's going to be our class 3 that we're going to talk about. However, if we don't care that much, and we're just trying to do just a base differentiation, cis and trans can work. Now, for rings, it is really important that you have 2 and only 2. So this is only for di-substituted rings. For example, if you have this third case here, where you just have a monobromo that's on a dash, you can't use cis and trans because there's nothing to compare to. And then in the case of where you have 3 or 4 multiple substituents, you don't know which ones are cis and which ones are trans, so you cannot use any descriptions there. So the cis and trans is kind of a very narrow description that you'll see every once in a while for rings or double bonds that are kind of on the simpler side. You can always use R and S, and you can always use E and Z, and those will always be right. So we're going to focus a lot more on the kind of class 2 and class 3. Double bonds are going to behave the same way. If you kind of think about, for example, some hydrogens here, I'll go ahead and draw hydrogens on these first 2. On the first one, where we have cis, both of those hydrogens are on the same side of the double bond. That's where that same or cis comes from. Where trans or opposite is where we see the hydrogens on our second one. Where this fails is if it's really hard to differentiate between your groups, and that's where we're going to really rely on our E and Z. So cis and trans we can use, but it's really, really limited. So our RNS and E and Z are going to be far superior in terms of descriptions. So let's go ahead and start with our R's and S's. You already know and are super confident on how to calculate your R and S configurations. We spent a lot of time in class doing this. You can go through, assign your CIP rules, and then find a handedness, right-handed or left-handed, and get your R and S. Now, to describe your RNS within your actual name, that's going to serve as a prefix, and it's going to sit in brackets. So, for example, here in this 2-bromobutane, if I have that bromo on a wedge, that's going to have an R configuration. It's going to be a clockwise rotation. Bromine is going to be the highest priority, ethyl 2, methyl 3. That's going to rotate clockwise, and our fourth group's in the back. So that's going to behave nicely as an R. Now, that's going to be in a bracket, or a parenthesis, I should say, and then you'll write your R. Now, if there's one and only one chiral center, you don't have to give any information. You can just simply say R, and you don't need any stuff beyond that. If you have multiple chiral centers, so for example, in the second one, where we have 2-bromo, 5-fluoro, 4-isopropyl octane, all of those, the bromo, the isopropyl, and the fluoro, all have chirality associated with them. So therefore, we actually need to know which one is R and which one is S. And for that, we write them all in order. So starting with the lowest locant to the highest locant. So if it's 1, 2, 3, all the way up to however many you have. And then what we'll do is we'll list the locant with your R and S. So in this case, for example, our bromo here is an R. So we'll write 2R. Our isopropyl here is at the 4 position and it's S. And then our fluoro here is in the 5th position and it's R. So you'll note that these don't match in terms of the same order because in the order for naming it's alphabetical. So the B of the bromo beats the F of the fluoro, which beats the I of the isopropyl. But in terms of the actual like descriptions in terms of your parentheses, all of these are all going to be in the same order of 2, 3, 4, 5, 6, lowest to highest. There is no alphabetical order, and it's going to be a number, which is the locant, and then the R or S for it. So the bromo is at the carbon that has the bromo off it is R, the carbon that has the isopropyl off of it is S, and then the carbon that has the fluoro off of it is R. So we list all of that there, where it's 2R, 4S, 5R, all brackets, no spaces, and then a hyphen as we go into our rest of our description. So you calculate your RNS per normal, and then just put that as parentheses all at the beginning. Now, the kind of new stuff that we're going to talk about is going to be our class 3, and these are going to be associated with double bonds. Now, typically when we think of a isomer, a stereoisomer, something that has some chirality associated with it, generally our stereocenters have been things like a single atom, like a carbon that has 4 different attachments. Now, double bonds can also serve as stereoisomers, even though they do not have 4 unique bonds attached to them. Each side of the double bond will have 4 groups, and we can use those to describe the orientation of where your groups are. And for this, we're going to have 2 new terms that are going to come in. These are both derived from German words, zusammen and entgangen, and that's where that E and Z is the first letter of each of those words comes from. Now, in order to be a stereocenter, there is kind of an important kind of consideration. And for each of these, we're going to kind of like divide the double bond in half. And we're just going to care about the left side versus the right side. On the left side, for example, where we have this A and B, those 2 need to be different. If they're the same, then we cannot. It's achiral. You don't have any stereocenters. They need to be different. And then on the right side, your C and D also need to be different. Now, the other ones are okay to be the same. So if A and C are the same, that's perfectly fine. They're on different sides of the line. If A and D are the same, that's fine. The same as if B and C or B and D, because they're different colors. They're on opposite sides of that double bond. But the key ones is our yellows of our A and B, and then our blues of our C and D cannot be the same. Those need to be different within that individual like color group. Now, the descriptions for our E and Z comes from this German word for entgangen and zusammen. For each of these, zusammen means together, and entgangen means opposite, and that's going to be a description of where your highest priority group goes. Now, between, and as we kind of had highlights there, so for example, your C and D are both in blue. When we think about priority, what we're going to do is we're actually just going to use our CIP rules, the Con-Ingal Prelog rules, same as we did with RNS, and we're going to rank what C is and what D is and compare those. Whichever one has higher priority is going to be the one that we're going to consider for our arrangement. So as we divide our double bond in half, we'll have groups on each side. If both of the groups on each side have higher priority that are like together, and that's where that word zusammen comes from, we are going to call that Z. So both of these are, for example, on top of the double bond. Often what I'll say is when I think of Z, I'll think of same side. Imagine the word same side, just the S's replaces it with Z's. Same side of the double bond will have the Z description. Now, in your case for your E or your entgangen, those are going to be on your opposite sides. So here, if your highest priority is on the top for the yellow and then the bottom for the blue, those are on the opposite sides, and that's going to be an E. You'll see that this will actually match your kind of like cis and trans. Anything that you would have called cis can be called your Z. Anything that you would have called your E, you could call your, anything you would have called trans, you could have called your E. So that's where your cis and trans are kind of like super narrow and only describe some, where here you can use your E and Z and describe all kinds of your double bonds. So let's get a little bit of practice for this E and Z and look at a few different structures that have double bonds. And we have 4 different examples here. And for each of these, our very first thing is just going to be to kind of divide our double bond and then focus on each side. So if I go ahead and start with number 1, and let's go ahead and focus on the right side here. My first thing that's attached to my double bond is my oxygen and my sulfur. So between these 2 different groups, we can run our CIP or our Con-Ingal Prelog rules and then have a priority. And that's going to be based on atomic number. And here, sulfur is going to have a higher atomic number than oxygen. So our sulfur is going to have our higher priority. If we do that same thing and we look over on the left side, our very first point of attachment is a nitrogen versus a carbon. There, our nitrogen is going to win out because nitrogen has a higher number than our carbon in terms of the periodic table. And here, if we then kind of use our double bond as another line here, we see that our nitrogen, which has higher priority on the left, and our sulfur, which has higher priority on the right, are on opposite sides here. They're on the kind of like different quadrants here, and that gives us this E as our description for this double bond. So this is an entgangen or an E configuration. If we follow that same type of process and look at this next one, dividing our double bond into our different quadrants here, and sometimes, depending on how this structure is drawn, that might be like rotated a little bit. So if I look over on my right side, my very first point of attachment is an oxygen and a carbon. In terms of priority, oxygen beats carbon, so our oxygen has higher priority. Remember, this has nothing to do with size. Yes, your carbonyl is bigger physically, but we only care about priority, and we look for our CIP rules at the very first point of attachment. So that's where our oxygen is going to beat our carbon. For our other one, we have a hydrogen, which is not drawn in, versus a carbon. Carbon is definitely going to win there. Between those 2, carbon has a higher atomic number than hydrogen in terms of our CIP rules. And here we see that our higher priority, the things that we've circled, are sharing the same face. So they are on the same side or same side. So we are going to use the Z descriptor for those. In terms of naming, what we'll do is we'll match the exact same process where we did with R and S. Instead of having an R or an S, we're going to do an E or a Z. And if we have multiple, we'll give locants for where they exist. So we treat the exact same thing as R and S, but here we're going to have E and Zs. Now let's go ahead and walk through the two last examples here. Let's just continue around clockwise, and we'll do number 4 first. I like to be a rebel. We'll be a little bit different. If I look at my, let's go ahead and keep the right side. Here we see each of these are carbons. And much like with our CIP rules, if we get a tie, we look at the next things that are connected to that. So if we wanted to even write this out, for example, this would be a carbon that is connected to a carbon, and a carbon. Exact same CIP rules that we use for our RNS. Lower down here is a carbon connected to a carbon, and a hydrogen. And here, when we look for points of difference, same. Our main difference here is going to be that carbon versus the hydrogen as the last point of attachment within that bracket. And here, our carbon is going to win out, so that tert-butyl will have higher priority than that isopropyl. Over on the other side, we have a carbon versus an oxygen. Here, we have our oxygen having higher priority. So these are also going to be Z for same side. They are both on the same side of the double bond. They're sharing that dash bond between them. Now, based on that, go ahead and pause the video for a second and try to solve number 3 by yourself. Use your CIP rules and then try to find out your priority. Now let's go ahead and double check our work here. On the right side, we're comparing an oxygen versus a carbon. That's the very first point of attachment. So our oxygen will win. On our left side, we have a carbon versus a carbon. Both of those carbons tie, so we're going to go ahead and do some comparisons. This carbon here is attached to a nitrogen, a hydrogen, and a hydrogen. The carbon here is the one that's yellow. The one up top is a carbon that's connected to a carbon, that's that red dot I just drew, and 2 hydrogens. These hydrogens are the ones that are not shown on our skeletal structure. In terms of our comparisons here, carbon versus carbon ties. Our first point of difference is this nitrogen versus our carbon. Nitrogen is going to win out. So this bottom amine is going to beat our carboxylic acid in terms of our priority, and therefore this is going to have an E. And much like how we do with R and S, we use our Kahn-Ingold-Prelog rules to find priority, see if those higher priority groups on the left and the right side of our double bond are going to be on the same side or opposite, and we use those to get our E and our Z. That E and Z is going to fit in a parenthesis before our name, the exact same as our R and S. And that's that one little extra thing that we do in terms of our naming to be able to differentiate between the multiple different possible stereoisomers that exist.